what I will do is I will take 20 minutes of lecture and then we will start this. So we have discussed functions of random variables. There are some special random variables, special distributions that are quite often encountered. So we looked at some of these special discrete random variables. Now we will look at some special continuous distribution values. There is one random variable called as the gamma random variable called as the gamma distribution. So the motivation is like this one. So you have, let us say, exponential random variable. So x I is an exponential random variable with a parameter lambda. You have many such IID x4 lambda random variables. We will call them as x1, x2 and so on. And let's say that of n of them. We are looking at the sum of some n IID x4 random variables. So where would you think that you would this kind of a requirement of adding IID exponential random variables might be imposed? For example, you have let's say a component or let's say light bulbs from the same manufacturers, and we have characterized them that their lifetime is exponentially distributed with the same parameter lambda. So what you do is you pick up one bulb and then put it into use, and as soon as it goes away, its lifetime gets over, you replace it by another one and keep doing up to n bulbs. Then you look at the total period over which these n bulbs have lasted. So it will be the sum of the lifetimes of n components or n bulbs. So each one is an exponential random variable with the parameter lambda. They are all independent, they are all identical. So the total time period over which n components have lasted is the sum of the lifetimes of the individual components. To take another example, you go to a bank, then if you want to get some service, you go to a clerk and then they may take the service time, which is can be modeled as an exponential distribution. But let us say your requirement is such that you have to go to not just one person, you have to go to 3 or 4 persons. Each service, it's of different phases. There are 4 phases of service. Each service phase is as the service duration exponentially distributed with a parameter lambda. So the total time you have to spend in that service station is the sum of 4 service duration, each one being exponentially distributed with a parameter lambda. So that total sum of IID exponential random variables can be modeled to be a gamma distribution. So this interpretation of n IID exponential distribution can also be generalized. N need not be, it can be a general function. Okay, when n is an integer, then this gamma distribution has a special name called as the Erlang distribution. It need not be an integer, it can be any arbitrary value, real value, positive value. In that case, we cannot view it as sum of n, but a generalization is also possible. So I will tell you how these things work. So let us say if a random variable x has a gamma distribution, then its density function is given by lambda e power of minus lambda x lambda x power alpha minus 1 by a function called gamma of alpha for x greater than or equal to 0 and 0 This is how it is defined. It looks very unlike the kind of distribution we have encountered so far. This looks little complicated. Henceforth, there are many such distributions we look at. All are little, it's not straightforward, but they all have some application. They are encountered in the system. Where this gamma function is defined as 0 to infinity x power alpha minus 1 e power minus x dx. So a gamma distribution can be used as a density function of a continuous valued random variable taking non-negative values. So x can only be a non-negative. For negative, it is 0. The density function vanishes. And for any given x, if you want to find the density, you plug it in this one, you get it. Where alpha is a parameter. So for different alpha, you will have different gamma distributions. So in most of the distribution, there will be a parameter. We have seen that in exponential also, lambda is a parameter, and binomial, Bernoulli, everything there is a parameter that is involved. So this is how it is. First, let us see whether this one is a valid distribution. For that, first we will look at the properties of this gamma function. So we will evaluate it by parts. So I will put it as x power alpha by alpha dx. Okay? So you will take this as u and this as a dv in your integration by parts. Then you will have e power of minus x into x power alpha by alpha between the limits 0 and infinity minus of. Again you have to differentiate this one. That will be again within this one. What you will get. And obviously this vanishes. And this becomes plus right? So look at this one. And we have defined alpha function as e power of minus x dx will be there. If it is okay. You see, x is a dummy variable. See, it goes away. Finally, you will evaluate to a value, some value, and the parameter only is alpha. Okay. So e power of minus x will be there. X power alpha minus 1, if it is there, then alpha. Gamma of alpha means x power alpha minus 1 will be there. Here, x power alpha is here. Otherwise, it is the same limit 0 to infinity, e power of minus x dx, everything is there. So this function is gamma of alpha plus 1. Okay. So it is just 1 by alpha into gamma of alpha plus 1. So that is it. We are looking at a property of gamma function. So which means that gamma of alpha plus 1 is equal to alpha times gamma of alpha. We can write it otherwise also. So this gamma of alpha, if you look at this one, you can again substitute, keep substituting it into alpha minus 2 into gamma of alpha minus 2, alpha minus 3 and so on. It looks very similar to a what function? Factorial function. In fact, if alpha can be a real number, the gamma function follows this. If alpha is an integer, say n, then gamma of n is nothing but n minus 1 factor. So gamma function is a function which is a generalization of the factorial function. That's all. A generalization of a factorial function. Well, now, having looked at this one, we will come back to this fx of x. Now, first what we will see is, I will show you different things. First, whether this is a valid PDF, that we will check. Why all these complex way of putting it will become clear when we look at that one. We will first see whether it is a valid PDF. Then we will see how our claim that sum of n IID random variables will have a gamma distribution, that also we will see. First, if it is a valid PDF, integral 0 to infinity fx of x dx has to be equal to 1. So again we will put this one, we will integrate this function. It goes from up to 0, it is 0. From 0 onwards only it is there. So it's actually not minus infinity, but because 0 below 0 it is 0. This one becomes 0 to infinity lambda e power of minus lambda x power alpha minus 1 by gamma of alpha into dx should be equal to 1. We will evaluate that. Okay. So we will take this one outside and then we will put, let us say, if you use the substitution, I am taking this outside, it's a constant. Lambda into dx is du, lambda x is u power alpha minus 1, and this is e power of minus u. Okay? This is how it will get translated. And what is this? What is this integral? Look at gamma of alpha's definition. Write it there. 0 to infinity x power alpha minus 1 e power of minus x dx. Instead of x, which is a dummy variable, we have u. E power of minus u power alpha minus 1 du. If it is there, it is a gamma of alpha. So that is equal to gamma of alpha divided by gamma of alpha, which is equal to 1. So what we are getting is this holds good. So first it is a valid PDF. Okay. Well, then if you want, you can just check the mean of that or expectation of this kind of a random variable, which is okay. But now we will do is okay. Yeah, we can also use it for general alpha, but now we will stick to Erlang distribution, which is a special kind of gamma distribution, wherein the parameter alpha is an integer n. Okay, for that we will do, because that interpretation will be more this one. So in which case the gamma of alpha becomes n minus 1 factorial. Clear? See, gamma of alpha, if alpha is an n, it becomes n minus 1 factorial. So this is how it is. Again, let us use lambda x is equal to u, lambda dx is equal to du. So we will get 1 over n minus 1 factorial, integral 0 to infinity. Okay, lambda dx we have got, that is du. Okay, e power of minus lambda x is there. Now there is also an x, and here lambda x power n minus 1. So I will take this x here, I will put one extra lambda and divided by lambda. So if I put by lambda, and that compensating lambda along with this x can be absorbed with this to get lambda x power n. Clear? So I want to raise it to n. One x is already this lambda, I am keeping it. Sorry, I will keep it. Or should I keep it? Or yeah, we will keep it because we need the structure. This lambda we will keep it. This x and one more lambda we will put it, compensate it by this. Now if you use the substitution, you will have lambda into this is du, this is e power of minus u, this is u power n. Okay, by one lambda is there, this also we will take it away. So we can even alpha itself, with that also we can work, there is nothing wrong in that one. So what is this one? What is this one? Huh? Gamma, if it is gamma function means gamma of n plus 1. Sorry, yeah, gamma of
n plus 1.
u power n. The one. Okay. Gamma of, and this is nothing but gamma of n plus 1, which is n factorial. Which is gamma of n plus 1, which is n factorial. Okay, that is equal to n by lambda. If we have used alpha instead of this generalization, I would have got this as, okay, this would have been instead of n minus 1, it should have been gamma of alpha. This would have been gamma of alpha plus 1. Okay, I would have got something like this one, 1 over lambda into gamma of alpha plus 1 divided by gamma of alpha. And gamma of alpha plus 1 is alpha into gamma of alpha divided by lambda into like this, which is alpha by lambda. This is what I would have got if I have worked with the generalized value itself. So finally what we are getting is, okay, the mean of a gamma random variable is alpha by lambda. Okay, or Erlang, this is the Erlang, is n by lambda. We have told that an Erlang distribution is nothing but sum of n exponential distribution. Each expo distribution has a expectation 1 over lambda. The sum of the expectation of the sum will be n times 1 over lambda, which is n by lambda. That is how it comes. Because you go through n exponential servers, each one service time is 1 over lambda, and the total service times expectation is 1 by lambda plus 1 by lambda n times n by lambda. That is how it comes. And we will see whether we quickly do this also. Why don't you distribute the answer scripts quickly?